Hello friends, we have discussed Numerical theory of free electrons in detail. In this lecture, we are going to verify some of the analytical results using simple Python codes. Let us start our discussion with density of states. So, how did we discover density of states? We know that thermodynamic property can be calculated by k-space integration of this form, where f of E is the Fermi function given by 1 divided by exponential E of k minus mu divided by kBt plus 1. The other function capital F of k depends on the property that we want to calculate. For example, f of k is equals to 1 for electron density and f of k is equals to h cross square k square divided by 2m for energy density. For example, we can calculate the electron density by calculating the integral of this form. Note that the integral is over k. Now, using E is equals to h cross square k square divided by 2m, we can convert the k-space integration to energy integration. And we can write n by v as integral of density of states times the Fermi function. And this integral is over the energy. Thus, we discovered density of states in the process of converting k-space integration to energy integration. Electron density is given by the integral of density of states times the Fermi function, where density of states for 3D electron gas goes as square root of E. Note that density of states is equals to 0 when energy is less than 0. Meaning of density of states can be easily understood by calculating the electron density at T equal to 0 Kelvin. At T equal to 0 Kelvin, electron density is given by integral 0 to EF dE times G. Note that since G of E is equal to 0 for energy less than 0, the lower limit of this integral is set to 0. On the other hand, Fermi function is a step function at T equal to 0 Kelvin. That is, at T equal to 0 Kelvin, f of E is equals to 1 for E less than EF and f of E is equals to 0 for E greater than EF. As a result of this, the upper limit of the integral is set to E of F. Integral is total area under the curve. As shown in the diagram, total area under the curve shaded in red is equal to the number of energy levels between 0 and EF. If we take a small strip of width dE, the area of the strip is GE dE as shown by the blue shaded region in the figure. Since the total area under the density of states curve represents the total number of energy levels, the small strip also should represent some small number of energy levels. Thus, G of E dE is equals to number of energy levels between E and E plus dE. Let us see, instead of getting density of states as byproduct of change of variable from K to E, is there a direct way of deriving density of states? Let me show a numerical scheme to get density of states. I show it for a 2D electron gas, and the same scheme will work for 1D or 3D electron gas. In 2D, energy is given by h cross square by 2m kx square plus ky square. We know that each point in k space represents an energy level. Filling K space with electrons is same as filling energy levels with electrons. For example, filling the 0, 0 point in K space is like filling the lowest energy level. Filling the 1, 0 point, and there are 4 such points of equivalent energy in K space, is like filling the next energy level, and so on. In the rightmost diagram, I show total number of states at each energy. For example, when energy is equals to 0, there are 2 states. When energy is equals to 1, there are 8 states. When energy is equals to 2, there are 8 states, and so on. Now we split the entire energy range in small energy strips of width dE. Finally, we count the total number of energy levels within the energy range dE. For example, in this case, within this energy range, we have 8 plus 8, 16 plus 2, 18 energy levels. This is the algorithm to numerically calculate DOS. The same algorithm will work for 1D and 3D. Let us write a code to calculate density of states for a free electron gas in 3D. We need to specify range of Nx, Ny, and Nz, and we take all of them to be equal to 100 as shown here. We run a for loop to get the total energy E as a function of Nx, Ny, and Nz. And the energy value is calculated here. We split energy in small strips of width dE for DOS calculation. For every small strip ranging from E min to E min plus dE, we count the number of energy levels in that energy range. This gives us the value of density of states. Finally, we plot density of states as a function of energy. This is the code for calculating DOS in 3D. Here we define the number of K points. This is where we define the energy intervals for DOS. We have created one array to store the value of DOS. Then we run a for loop to get the density of states. So in the for loop, first we define the energy interval, and then we run for loop to get the total energy. The total energy is calculated in this step. Then if the total energy for a given value of J, K, and L lies within the energy interval we defined here, then we just update our array for storing the value of DOS. And then we plot the density of states as a function of energy in this step. If you run the code, then this is what you will get. Thus, the density of states for 3D electron gas fits very well with the line square root of E. This is shown by the red color. We already know that for 3D electron gas, G of E goes as square root of E. Thus, the code managed to find the density of states for a 3D free electron gas correctly. Write a code to find the density of states for 1D and 2D free electron gas. In this slide, I show the density of states of a 3D, 2D, and 1D free electron gas side by side. Note that in case of 3D, the density of states goes as square root of E. In case of 2D, the density of states is a constant, and in case of 1D, the density of states goes as 1 by square root of E. Let us derive density of states for 3D and 2D free electron gas. In case of 3D, we take a sphere, and volume of the sphere in K space is given by omega 3D is equals to 4/3 pi k cube. In case of 2D, we take a circle and area of the circle in k space is given by omega of 2D is equals to pi k square. Now we know that the volume occupied by a single point in k space in 3D is delta k 3D is equals to 8 pi cube divided by V. Similarly, in case of 2D, the area occupied by single k point is delta k 2D is equals to 4 pi square divided by A. Now we divide omega 3D by delta k 3D and multiply by 2 to account for Pauli's exclusion principle, which allows 2 electrons per state. If we do that, then we get k cube is equals to 3 pi square n in case of 3D. Similarly, in case of 2D, we have to divide omega of 2D divided by delta k of 2D and multiply by 2 to account for Pauli's exclusion principle. And if we do that, then we can derive k square is equals to 2 pi n. In case of 3D, small n is equals to number of electrons per unit volume, and in case of 2D, small n is equals to number of electrons per unit area. Now we replace k by E using this equation such that k is equals to square root of 2me by h cross square. If we do that, then in case of 3D, we get n is equals to 1 by 3 pi square, and in place of k's, we just write square root of 2me by h cross square whole power 3. And then we can calculate dn by de, which is equal to 1 by 3 pi square into 3 by 2 2me by h cross square whole power half times 2m by h cross square. And d and d is the density of states. Thus, we can express density of states in case of 3D free electron gas in this form. Similarly, in case of 2D, we just write n is equals to 1 by 2 pi, and in place of k square, we are just going to replace 2me divided by h cross square. And in this case, we get dn by de is equals to m by pi h cross square. Using similar method, you can derive the density of states for 1D free electron gas. This is left as an exercise for you. Now that we have figured out how does the density of states look like for 1D, 2D and 3D free electron gas, we can plot Fermi function times density of states at T greater than 0. Let us do it for room temperature. At room temperature, kBT is equals to 0.025 electron volt, where kB is the Boltzmann constant and T is the temperature. Let us take Fermi energy to be equal to 1 electron volt. We define the Fermi function here, and for a 3D free electron gas, density of states is equals to square root of E. Then we plot energy versus Fermi function, energy versus density of states, and energy versus Fermi function times the density of states. The plots for 3D, 2D and 1D looks like this. Now, Fermi function differs from its limiting values 0 and 1 only in the region E close to the Fermi energy. As a result, for E less than EF, Fermi function times density of states is almost equal to density of states except for a region E very close to the Fermi energy. You see that the orange curve is the density of states and the green curve is the density of states times the Fermi function. And for E less than EF, for most of the regions, the orange curve and the green curve are identical. On the other hand, for E greater than EF, Fermi function times density of states is very close to the Fermi function except for a region E close to EF. In the plot, the green curve is the density of states times the Fermi function and the blue curve is the Fermi function. And you see that for E greater than E0, they are identical and they differ only in a region where E is very close to the EF. Thus, to understand the behavior of free electron gas at T greater than 0, we need to mainly focus in a region close to the Fermi energy. To understand what changes in finite temperature, we plot Fermi function times density of states at T equal to 0 and T greater than 0. We cannot take T exactly equal to 0 because in that case, inverse temperature 1 by kBT becomes infinity. Thus, we take a very small temperature kBT 0.001 and compare it with room temperature where kBT is equals to 0.025 electron volt. In this plot, the blue curve is Fe times Ge at a very low temperature and the orange curve is Fe times Ge at room temperature. Note that Fe times Ge is identical at T equal to 0 and T greater than 0 except a region close to the Fermi energy. That is, they are identical in this region as well as they are identical in this region, but only in the region close to the Fermi energy, the blue and orange curve differ from each other. Here I have shown it for a 3D free electron gas. You can write a code for 2D and 1D free electron gas. Let us find out the fraction of electrons getting excited above the Fermi level at T greater than 0. Total number of states is given by the total area under the curve Fe times Ge. Number of states above EF can be calculated from the area as shown here. In the code, we calculate the total area under the curve here and we calculate the area of the hash region here. Let us run the code. This is the code for counting the occupied states above Fermi energy at T greater than 0. This is where we define the range of kBT and we start at a very low temperature 0.002 and we go all the way to the room temperature. This is the array where we are going to store the number of occupied states above the Fermi energy. The number of states at 0 Kelvin can either be calculated by finding the total area under the curve or it can be obtained from the analytical result as shown here. Then we find the area under the curve of the hashed region that is above the Fermi energy in this step. And this area is equal to number of occupied states above the Fermi energy. Let us run the code and find the number of occupied states above the Fermi energy at T greater than 0. Clearly, fraction of electrons excited above the Fermi level increases linearly with kBT. In theory lecture, we argued that delta N divided by N, that is the number of electrons excited above the Fermi level divided by the total number of electrons, goes as kBT times density of states at the Fermi level. In our code, density of states at the Fermi level is a number which is close to 1. Thus, our code validates what we argued in the theory lecture. I showed for a 3D free electron gas. It is left as an exercise for you to write a code for 1D and 2D free electron gas. Total energy can be calculated by finding the area under the curve E times Fe times Ge. Two of them, one at a temperature very close to 0 and another at room temperature, are shown in this diagram. The energy difference can be calculated by finding the difference of the area under the curve shown in orange and blue color. The code given here is going to generate the plot as shown in this slide. Let us write a code to calculate the energy difference between t equal to 0 and t greater than 0. This is where we calculate the area under the curve at t equal to 0. And this is where we calculate the area under the curve at t greater than 0. We store the energy difference at different temperature in an array. This is the code for calculating the energy difference for temperature t equal to 0 and t greater than 0. This is where we define the temperature range. And this is where we calculate the total energy at a temperature which is very close to 0. Then we run a for loop and we get the total energy at t greater than 0. This is where it is done. Finally, we store the energy difference in some array and then we plot the energy difference as a function of kBT square. So let us now run the code. Clearly, delta E is a quadratic function of temperature. Let us go back to what we argued in the theory lecture. Number of excited electrons is given by kBT times the density of states at Fermi energy. Now, excess energy above the ground state of these electrons is kBT. Thus, delta of E is kBT times G of F times kBT, that is kBT squared times G of F. In our code, we indeed see that delta E is a quadratic function of temperature. Thus, the code provides validation of what we argued in the theory lecture. I showed for a 3D free electron gas. It is left as an exercise for you to write a code for 1D and 2D. We know that at T equal to 0 Kelvin, the chemical potential is equal to the Fermi energy. In numerical exercises, so far we have assumed mu is equals to F even at a temperature which is greater than 0. Let us assess how good or bad is the assumption. From Sommerfeld expansion, we know that the chemical potential for a 3D free electron gas decreases quadratically with increasing temperature. However, Sommerfeld expansion is an approximation. Is there a direct way of calculating mu? We know that at T equal to 0 Kelvin, the number of electrons can be obtained by integrating density of states between 0 and F. At T greater than 0, the number of electrons can be obtained by evaluating this integral. In case of a constant volume process, N naught should be equal to N. Now, from this equation, it is clear that for a given value of temperature, N, the number of electron, depends on the value of mu. This is going to be our algorithm for calculating mu as a function of temperature. At a given temperature, we are going to start with a guess value of mu, and we are going to tune it until we reach a point where N is equal to N naught. Let us write a code to get mu as a function of temperature. We shall consider 3D free electron gas such that density of states is equal to square root of E. Total number of electrons at t equal to 0k can be calculated by integrating density of states from 0 to the Fermi energy, and it is equal to 2/3 times EF to the power 3/2. N naught is calculated here in the code. At some temperature greater than 0, number of electrons can be calculated by integrating density of states times the Fermi function. This integral is calculated here in this user-defined function. We start with some initial guess value of mu. For example, we can start with a guess value mu, which is equal to EF. We calculate the number of electrons for the guess value of mu and verify whether it is equal to N naught or not. We vary mu until we reach a point where N is equal to N naught. This is done by using a while. Once this condition is satisfied, we have the value of mu at a given temperature. We do it for a wide range of temperature where the temperature is varied using a for loop. This is the code to calculate mu at different temperature for a 3D free electron gas. This is where we define the range of kBT, and this is where we define the Fermi energy. This is where we calculate the number of electrons at t equal to 0 Kelvin. In this user-defined function, we calculate the number of electrons at a finite temperature for some guess value of mu. We start with a guess value of mu equal to EF, that is the Fermi energy. Then we have a while loop where we calculate the number of electrons at some finite temperature for a given value of mu. Then we check whether NT minus N naught is greater than this number or not. Once this condition is satisfied, that is when the value of NT, the number of electrons at finite temperature, is very close to the number of electrons at 0 temperature, at that point we decide that the convergence is achieved and we store the value of mu in some array. Finally, we plot mu as a function of kBT. So let us run the code. This is how mu varies as a function of kBT. We can even plot it as a function of kBT square. So let us do that. So previously we were plotting mu as a function of kBT. Now we plot it as a function of kBT square. And then this is how the plot looks like. Thus, we get a curve if we plot mu as a function of kBT. Further, by plotting mu as a function of kBT square, we get a straight line which confirms that mu decreases quadratically with increasing temperature. The outcome is same as obtained from the Sommerfeld expansion. Note that the room temperature is around 0.005. Thus, at room temperature, mu hardly changes from F. So our assumption of mu is equals to EF in previous numerical examples is not too bad. Let us discuss an example where Sommerfeld expansion is going to fail. We know that using Sommerfeld expansion, we can write the electron density at finite temperature in this form. Thus, if density of states is a constant, for example, in a 2D free electron gas, we cannot use Sommerfeld expansion because G dashed is equal to 0. In that case, Sommerfeld expansion always predicts that mu will be equal to EF for any temperature, which is not correct. In such cases, we have to find mu not from Sommerfeld expansion, but using some other method. For example, the numerical method discussed in the lecture.